Hello everyone, welcome back to another lessons learned video. Today we're going to discuss pKa in acid-base reactions in organic chemistry. So pKa is basically a measure of how acidic a molecule is when dissolved in water. And the lower the pKa is, the more acidic it's going to be. So here I'm going to give you a list of some molecules and their pKa values. And you should write this down because these are the ones that you'll commonly come across in the organic chemistry classes. So here, the first one is sulfuric acid. That one is the lowest pKa. It's -10, which means it's the most acidic molecule of the ones we're going to talk about. Then hydrochloric acid is -7, and then this is a protonated ketone here, and that's -3. What we have here is the hydronium ion. It's the basically the type of acid that forms in water when you dissolve any acid in water. Hydronium ions. We then have, let me go on this side. We then have a carboxylic acid. So whenever you have this functional group anywhere, that has a pKa of 4. And then we have, let's say we have two ketones that are next to each other. This hydrogen here, right, this one, is going to have a pKa value of 9, right, and only for that hydrogen. And for the other cases, it's this hydrogen. Its hydronium looks like this in reality, right? So it's really just one of these hydrogens. Here it's this hydrogen. Here it's the hydrogen. There's only one there. And then it's just one of the hydrogens in sulfuric acid. Any other two in sulfuric acid. Then we're going to have a molecule called phenol. So it looks like this. There's a benzene ring. I could have drawn way better. And there's a hydroxyl group on it. This hydrogen has a pKa of 10. So I'm going to delete this list and keep moving on with more molecules. So make sure you have this down. Okay. So water molecule, water, all right, is going to have a pKa of 15. So water, excuse me, I need some of that. So water has two hydrogens. Any of these two hydrogens it can give away has a pKa of 15. If we have an alcohol, right, the proton or the hydrogen on the oxygen is going to have a pKa of 16, so slightly less a weaker acid than what we had there with the water. And then we have also, we can have a ketone, and then the hydrogen, so this carbon here has really 3 hydrogens, but the pKa of any of them would be around 20. So if it loses this hydrogen, this oxygen can resonance with it. Now, if we have a triple bond, and we have a hydrogen attached to the carbon that's attached to the triple bond, that hydrogen or that proton is going to have a pKa of 25. Now, if we have ammonia or any molecule that has nitrogen-hydrogen bonds, right, one of these hydrogens would have a pKa of 38. Now, if we have a double bond and say one of the carbons on the double bond has a hydrogen, that proton is going to have a pKa of 45. And if we just have normal carbon-carbon bonds and there's a hydrogen on one of the carbons, that hydrogen is going to have a pKa of 50. So make sure you have those down, and those are probably the ones that are most useful in organic chemistry classes. So now let's get into an example problem of how we can apply the principles we learned there. Let's say we are given a problem where we are doing an acid-base reaction, and we're doing it with a molecule that looks like this, and we're doing it also with hydroxide. Hydroxide has a negative charge. What would be the outcome of this reaction? Would these two react, or would they not react, is the question. So to determine that, it's best to conceptualize this as an equilibrium process. So as opposed to drawing a straight area, which I did, you can draw an equilibrium arrow. And you should do the reaction and determine which one is the base and which one is the acid. So in this case, this one is the base. So this is base, and this molecule is the acid. Now, the acid has a lot of hydrogens, right? It has hydrogens here, 2 more on that carbon. It has a hydrogen here, really 2 there, and hydrogens here. Which one would be the most acidic hydrogen, or the most acidic proton? Meaning, which one has the lowest pKa value? So we're asking the question of which hydrogen is easiest to, which hydrogen is easiest for this hydroxide to pick up? And the answer there would be this hydrogen. So if you think back to the examples we had, right? If you had this molecule, it doesn't matter what's attached on the left side. If there's a hydrogen on here, this has a pKa of 20. So this hydrogen has a pKa of 20. Now, if you have 2 ketones with a hydrogen between them, that hydrogen has a pKa of 9. So the pKa of this hydrogen is actually 9. So when this hydroxide wants to choose which hydrogen to take, it's going to choose to take the one with the least pKa value, the one that's easiest to take. So it's going to come in and attack this hydrogen, and the electrons are going to go back to that carbon. So the outcome that we're going to get is a molecule that looks like this. There's an extra lone pair on that carbon, so there's going to be a negative charge on it. And then the hydroxide is going to turn into water. Right? Instead of OH, we're going to have OH2 or H2O, which is just water. So we used that right there. Now, in the products, we have the conjugate acid and we conjugate base. Actually, conjugate acid is the water, conjugate base is this thing. Now, looking at the acids, determine the pKa value of the acids. So, for the acid that we had in the reactants, we had a hydrogen with a pKa of 20 and one hydrogen with a pKa of 9. You want to pick the one with the lowest one. So, for this acid, it was a pKa of 9. For water, we remember from our list, it has a pKa of 15. So now the question is, in this equilibrium situation, would the equilibrium favor the right side, meaning the products, or would it favor the left side, the reactants? So the way we can answer that is a general rule you can just memorize. It's always going to go toward the higher pKa value. Right? The higher pKa value acid is more stable than the lower pKa value acid, and the conjugate base of this acid that has a pKa of 9, right, is more stable than the conjugate base of the acid that has a pKa of 15. So it's always going to go toward the higher pKa acid. So this process would have an equilibrium error that looks like this. We're going more toward the right side than we are toward the left side. So this is a product favored reaction. So now let's talk about the same type of question, but a different example. Let's say we are given an alkyne, so a triple bonded molecule. And this is going to react with NH2. NH2, known as amide, or you can call it azanide as well. So if you react these two, first of all, find the most acidic proton in the acid. So this is going to act as the acid. This one has a negative charge, so it's going to be the base. Which hydrogen, which proton in this molecule would it like to attack? There's really just two options. You can either attack one of the hydrogens here, there's going to be 3 there, or it can attack this hydrogen. The hydrogen on the left side, they're basically connected to just a normal alkane, so these are going to have a pKa of 50. But this one is going to have a pKa of 25 because it's attached directly to a carbon that's in a triple bond. So what's going to occur is that the lone pairs on this nitrogen are going to attack this hydrogen, and then the bonds of that carbon hydrogen bar are going to go back to the carbon. So at the end what we get is an ion like that, plus an extra proton or extra hydrogen on this NH2, so that would be NH3. And this would be the conjugate base, this would be the conjugate acid. So now what is the pKa of our conjugate acid, right? This NH3. If you remember the list, you can try to recall it if you want. It's going to be 38. Right? So the acid had a pKa, the lowest pKa proton had pKa of 25. This one has 38. So therefore, because of that, the reaction wants to go toward the higher pKa value. So it is going to be a right-sided favored reaction. So let's go over our last example problem now. So here we have another similar alkyne, but here it's reacting with hydroxide ion. What would happen in this case? So go ahead and try this problem on your own. So first of all, determine the most acidic proton in the acid. Draw the conjugate base and conjugate acid, and determine which would the equilibrium shift toward the right or the left. So in this case, the most acidic proton in the acid is the same one as before. It's going to be this hydrogen. This has a pKa of 25, about 25. So this hydroxide is going to attack that, and then it's going to lose those electrons, and they're going to go to the alkyne. So this is our conjugate base. Our conjugate acid would be hydroxide, or OH, with an extra hydrogen. So that's just H2O, or just water. And water has a pKa of 15. And that's the conjugate acid. So in this case, we want to go toward the higher pKa value side. So we're going to go from here to there. That means that this is going to be a reactant favored reaction. So the equilibrium area would point a little bit toward the products, but more so toward the reactants. So this is going to be what it looks like. So if you leave, the equilibrium position lies far to the left, because the left side is more stable than the right side. So I hope that was helpful, and thank you for watching.